the first lecture, somebody has asked about these questions about will these linear functions be actually a reasonable thing to do in a particular learning context, or you were talking about generalized linear regression last week, and maybe the question that you could ask is, okay, so I have this opportunity to use, I don't know, quadratic functions, cubic functions, or I don't know, sinus functions, cosine function, all kinds of weird stuff. So should I put it like all in my learning system, like everything, or should I just use linear regression, like plain and old? And so today, what we are going to do, today, I think this lecture and the next lecture, we are actually going to talk about why it is, for example, bad idea to like put everything you want, to see inside in your learning system and try to work with that. So, anyways, let's start. So, so by now you know that every learning system needs to go through some kind of training, and when you have training, after training you see what after training? That's the question. What you can
vector parameters.
Okay, so you have some. Actually, well, for linear regression you see vector of parameters, but in general you have some kind of set of functions, and yes, the answer from the training is one of these functions is chosen as something that it will be used in your predictions. What can you say about this one function? How well does it work?
You can evaluate it on some other data.
Okay, but when you don't have any other data at the moment, like you use everything for your training. Well, you can say something. You can say how well your trained function, your chosen hypothesis works on the training data, right? You can characterize, you can compute the error from the training, and you can figure out, yeah, okay, so there is some kind of error per example or something like that. So is it, if you have a low error, is it good or bad? Or if you have high error, is it good or bad? Any thoughts on this?
Because high error is usually bad all the time, and if a low error, it can depend. So if you overfit or underfit.
Okay, so you're mentioning things that we are going to talk about today, overfitting and underfitting. But so high error is, you say high error is bad. Why is high error bad?
No, if there are lots of outliers, then you will have higher.
Yes, so for example, if there is if the data doesn't fit the function particularly well, if there is lots of outliers, you may have high error. So high error is not necessarily bad. Low error, you said, it depends, and we will see that sometimes actually low error isn't actually a good sign. So anyway, you can estimate, you have a training data, you have your training process, and you can estimate how well the function that comes out of the training process actually works, how well it works on the training data. But we are not really interested in that. And there can be a big difference between how it behaves on training data and testing data. So what we are interested in how well the function works on new data sets. And so the question is, can we say anything about this? I mean, so for example, right? I am now teaching you some basics of machine learning. You come to the exam, and I will start asking you about, I don't know, politology. Will you do particularly well on that exam? Well, some of you do because you have some background, maybe you are interested in politology, but most of you won't, right? So the question is whether we can somehow connect the something that we see on the training data with something that we actually will see on the testing data. And so this is this thing whether the performance on the training data actually transfers to the testing data. This has actually a name. It's called generalization. So we are really interested in whether when we are building a machine learning system, we are not only interested how well we can fit the particular function to the training data, but we also care about whether this will generalize to the testing data sets. So if you take an example, you can have let's say we have an example where you have this is the standard one-dimensional training, I don't know, prices of the apartments or whatever, and you have data set, training data set, which looks like this. Okay, and now you say, okay, maybe let's try linear regression. So that will fit some linear function through this. That will be, I don't know, something like this. Okay? Is this a particularly good hypothesis? Well, it depends. I mean, if this is if the underlying data set looks like that basically the prices of the flats come, below some square footage are something and above are something else, then it's probably not a very good estimator, right? Because anything like here and here and here, this wouldn't be a very good estimate. And this is why we are not getting a good estimate from this linear regression.
Because our model is not complex enough to capture the...
Yes, so we would really like to have some more complex function that could model this, right? Because there is no linear function that would actually model this scenario. So this is actually called what you have mentioned. This is actually called underfitting. And intuitively this says, okay, we don't have complex enough models that will work for this scenario. And I mean, this is just an introduction, so we'll actually do more formal stuff, this more formally in a moment. Okay, so let's say I say maybe I want to use more complex functions like maybe 10th degree polynomials, right? That's a great idea. So anybody can say what the predicted function will be if I use like 10th degree polynomials for this with this training data set. I will look something like this. Okay. This will be my predict. This will be some. I will learn a function like this. Actually, the training error will be 0. In this case, because I mean, if you have 10th degree polynomial, and if you have like 5 training points, then I mean, you will basically find the polynomial that will fit the data perfectly. So that sounds great, right? We have a zero training error. is this a good predictor for the prices of flats? I mean, not really. I mean, nobody in his right mind would actually use this to predict flat prices. So this is the case where you have a little like a small number of training examples, and suddenly your set of functions from which you were choosing from is too large to be actually trained from this set, right? And that's called overfitting. And as you have said before, this is, I mean, the sign of, for example, if you have a training error 0, that's actually a pretty good sign that something is wrong. Okay, so, but now I'm just, talking, just giving you some nice sounding words, but we don't really know what they mean. And so the question is, can I actually say something about all of this in some math way? Actually compute something, say something about how well the function that I have chosen in a training will perform on a testing set. So any ideas what I would need to do? I mean, one thing that I need to do is I need to somehow establish the connection between the training and the performance afterwards, right? Because as I said, if I just don't give you any other information, anything else, I mean, I can really go and teach you machine learning and then give you an exam on politology. And this is, I mean, if I do that, I mean, no training, no learning has any chance of doing anything reasonable, right? Because I just didn't tell you anything about politology. So I need to somehow establish how the training set is chosen and how the testing set will look afterwards. What I will test and bring some connection. And so this actually has a fancy name. It's called stochastic model of machine learning. And it has some kind of assumptions. And so one assumption is that that the world is not something unspecified like here, but we need to make some assumption about how the data, what is the process, how the data is generated. And the idea is that there is some kind of probabilistic distribution. So we assume there exists a probabilistic distribution. Let's call it PXY. So this is a probabilistic distribution that goes over all possible inputs, all possible input vectors, and all possible target variables. Okay, and so the question is, what's reasonable probabilistic distribution that characterizes, and this is actually something that characterizes the world in this case. Okay, so I am saying that anytime I am getting a data point from a data set, I will actually ask this probabilistic distribution, and it gives me one from the probabilistic distribution. Okay, so this actually characterizes a little bit our world. And the question is, what's the reasonable assumption about this probabilistic distribution? What kind of probabilistic distribution I might want to consider for my Okay, so you say maybe some Gaussian distributions or something like that. And actually some part of machine learning theory is actually focused on things where we assume that everything is some mixture of Gaussians or something like that, and then we sort of try to build things on this or there is some there is assumption then we have a function there that is already in our training set and we just added some Gaussian noise or something like that. But we actually won't do that here. It's actually not a reasonable assumption. I mean, we don't know that the data sets that we will work with are actually, mixtures of Gaussians or something like that. We don't know actually anything about those data sets, right? So the interesting thing the interesting assumption that is made here that there exists such a probabilistic distribution, but we don't need to know it. We just need to know there is some random process by which we can, the only thing that we need to know about is if we ask for a data point, we can get it. And there is a certain probability of getting this data point, and that's it. So this distribution is unknown to us in most of these questions. So why is this important? How does this gives us connection between training and testing? Well, for example, if I talk here about random, you can imagine how the lectures goes. Like I stand here and talk about random stuff, right? I sample it from this distribution, right? Like machine learning theory here, linear regression there, support vector machines. We'll be talking about them a lot, and things like neural networks. I can order them in any way I like. Basically, I'm just giving you independent data points, right, on the lecture. And now, can it happen that I will ask you a question about politology in the exam? What do you think? In this model, exam is testing part, right?
There's non-zero chance that you will.
Okay, yes. I mean, there can still be a question about politology on the exam, but there is a low probability of actually getting one. If my lectures are random samples from this distribution, right? So if I would give, if there is a high probability of politology getting into that mix somehow, then I would also talk about politology in the lectures at some point with high probability. Yes?
What is the training data set in the exam? Our example data set is about politics.
Sorry?
What if the training set in the exam, our example set, is about politics?
Well, if the training set is about politics and I am talking about, it's extremely improbable that I would be talking all the time about machine learning in these lectures, right? If the distribution, again, so the process works as follows. The training set is generated. So training sets are just independent samples from Pxy. Okay, so instead of having some kind of continuous lecture here, I'm basically saying, okay, so I'm just giving you random samples worth of 20 lectures or so from this distribution. And so testing testing is also done in a sample from Pxy. So if I talk, if the training set is large enough, if I talk to you for long enough, by giving you random factoids from this distribution, then you will learn enough about this distribution so that the probability of getting something that is that I was not talking about in lectures in the exam is small. So that's the idea. You still can get a polytological question, but it's with low probability. Okay, so why is that important? You know, if you get a polytology question on an exam, it's like you're screwed anyways, right? Even if it's with low probability. So why is this interesting? We will basically assume that this stochastic model is true, that this stochastic model underlies our sampling of the data. And so what we will be talking about, we will be not talking about, you know, like every one example can be somehow bad, right? Every one example can go somehow wrong. But we will be talking about expected values. So we will be talking about what's expected error and things like that. So now I have a question. Who didn't have any probability so far? Don't be afraid. Okay, good. So we will review some part. So now for those of you who had, there will be a little bit of boring part because we will be reviewing some part of probability. So I'm starting to talk about, you know, expected values and things like that, and so I need to say what they are. Okay, so how this all works? Maybe let's switch to boards. So we will be talking about, you know, about expectations, expected values, etc., etc. In Slovak, this is stredná hodnota. And so there is something called random variable. We will denote them like x, y, z, and so in capital letters. So this is random variable. And this is the random variables is simply something that gets its value from some random process. For example, by sampling from this distribution pxy that I was talking about. Okay? So for example, you can have a random variable that represents a roll of a dice with you know, six possible values, 1 to 6. Okay? So you roll the dice, and that roll of dice is represented as random variables. Once you roll the dice, it gets its value, like it's like 3. Okay? But what I'm asking is, what is something called expected value? So this is expected value over variable x, random variable x, and from x. Okay? And so this is basically value. I mean, it doesn't make much sense with random variables to talk about a particular one value. Okay? But what it makes sense is about what happens when you do it like do the lots of rolls of dice. Okay? So in this case, my expected value will be something like as follows. I will take and I will roll the dice once, twice, 3 times, 4 times, and so on. And I will keep the scores, and I will compute the average over all the scores. And since I like it so much, I like rolling dice, right? It's exciting. I will do it like for infinite amount of time. Okay? So I will just roll dice, and eventually I will get, you know, some kind of value. So for the dice, what this value will be? 3.5. Why not 3? It's average. So basically, if I think about it, this like you know, I have told you how this is done, and now I can think, okay, so maybe this probability of 1/6 I get 1. This probability 1/6 I get 2. This probability 1/6 I get 3. And so on, with probability 1/6 I get 6. Okay? And so if I compute that, I get 3.5. So here you can actually see that expected value is not something that you get most often on the random variable, right? Because I mean you never get a 3.5 in when you roll dice. Okay, it's sort of average over all of the tries, but you might get the actually value that you will never actually get. Okay, so that's the expected value. So, okay, now I can do something like this. So here, I don't say I'm doing like so now what I did, I said I'm still doing expected value over all possible over distribution over the random variable x. But now instead of keeping like a score that I get, I also square it for them. Okay? So instead of like recording 1, I record 1. Instead of recording 4, I record 16. So what will be expected value here? Any ideas? Yeah? Actually not. So basically, instead of, this doesn't necessarily, sometimes it holds that you can actually square the expected value, but it doesn't hold always. What you really need to do, you need to repeat this thing. So instead of writing x here, you will write x squared, so it will be 1 6 times 1, 1 6 times 4, 1 6 times 9, plus 1 6 times 36. And you will get something like, approximately something like 15.2. So in general, if you have expectation, basically expected value of x over some function of x is simply sum over all possible values of x. This function, the thing that we are recording, times the probability that I'm getting x. Okay, there are a couple, without actually going into proofs and things like that, there are a couple of rules that you can actually use. So for example, there is something called linearity of expectation. So if you have like expected values of sum of two variables, then it's simply sum of these two things. But what doesn't actually necessarily hold is that often is not equal to x times y. Okay, so this you can use, this you don't. So it starts to, since I'm talking about these expectations, now it sounds like, okay, so our guarantees won't be something absolute here, right? So I'm going to just tell you, if I have this performance on training set, I can get, if I try it like gazillions of times, I can get this performance on the testing set on average. But it doesn't mean that, one particular example won't be a disaster. It just tells you it won't happen too often, basically. Okay, one note that we need to talk about is that most of the time, I mean, this is all good for discrete random variables. Most of the time, we actually won't be working with discrete random variables. So we need to do some generalization of this to continuous variables. We won't like dwell on it too much because it's complicated. But in general, I mean, what works for most of the time, if you actually don't have experience with continuous random variables, just think about discrete variables and then replace, probability with density, which I will define in a moment, and sums with integrals. And that then most of the time it works. It just works that way. Basically, for continuous random variables, we have something called density of the variable. We don't have a probability of each of the values because if you take any continuous random variable, basically probability of getting this particular one point is usually 0, unless it's a very degenerate probability distribution, like like a discrete, like it only gives you discrete values, right? Or most of the time it gives you discrete values. Then it's most of the time it's 0 in most of the distribution. So we have instead something called density of the distribution of random variable x. And so basically this density basically means that it doesn't tell you anything about the particular value or nothing interesting. It's only interesting if you talk about intervals. So if I ask what's the probability that I will get the value of x between a and b, let's say, between two values a and b, and then it's going to be integral of px in the interval a and b. So intuitively, you can imagine this as follows. You can basically say, okay, let's divide all the values of x. Let's say it's like real values, real valued variable. Okay. So then you can divide it into small pieces of, like these are all possible values, and you can divide this into small intervals. Each one has the size delta. Okay? And for each interval, you have some probability. I mean, now it's actually not necessarily 0. Now you actually can get some decent. You can say, okay, I have probability of getting the value inside this is something reasonable. And you say, and you divide this probability by delta, by the size of the interval. Okay? And then you take, and because you liked it so much, you divide it into like smaller delta, and so on. And as this goes into 0, as delta goes to 0, you get to the density of the probability distribution. And so then, if you have a expected value of some function over values of x, I said replace sum with integrals. So basically this is integral over values of x fx times px. Okay? So as I said, replace the sums with integrals. That's it. And the probability with probability density, and you are done. Okay, I think that's all about expectations that we will need to know for now. So let's start thinking about where the errors can come from. So, I will get this training example and I will get some error, right? But this error from the training example comes from several sources. So what are the sources of those? So basically, the first thing is that I have So let's say that there is some function here, and that's the best ever function that you can have, like from all functions that existed. Okay, so I will. Say this is h squared x. So what do you think? Does this function have 0 error? Like best function, not from like some limited set, like from all functions. So who thinks that it has 0 error? Okay, one, only one. Come on, you have to think something, so you have to choose. You know what the second alternative is. So who thinks that it has 0 error? Okay, doesn't matter actually. Okay, who thinks it doesn't have 0 error? Why do you think it doesn't have 0 error?
Because if the distribution is uniformly random, then you can take any function and there's no error.
The question is distribution of what? Because if I said that for every x there can be only one y, then it would actually have a 0 error, right? Then I would just give, for this x, I would simply give you. I mean, my function would give you for that particular x will give you particular y, okay? But unfortunately, it may happen that actually there is not only one possible y for every x. So there is some inherent uncertainty even in, basically the data, what I'm trying to target, the thing that I'm trying to target is not actually uniquely determined by the attributes that I have. For example, if I'm talking about prices of apartments and I'm talking about square footage, then the price of the apartment is not always the same if I have the same square footage. So then I can have, so already there is an error here. I have this function that is like the best function ever. So this function h squared x is basically function function that is a function from all possible functions, okay? So that if I take from this distribution, if I take a sample x and y, x are attributes, y is the target variable, then I take and take value of h, and I do squared. So that's the best function you can get. Okay? Basically it tells you on at every position where you for every attribute just get. It's not clear that it's so, but believe me that it's so that you take actually average over or expectation over all variables. So this is simply for every x. This is Lyman over I. So I will basically take so basically what I will do, what this notation means, okay, is that I will take a particular value of x, and I will only say, okay, just give me y's that I have a fixed x and just give me some corresponding y. Okay? So you can imagine this very simply. You just, if I just can ask this probability distribution to get me a pair of x and y, I would just throw away all the tries where I don't get x. Okay? So then I get a distribution over y, over the target variable, and this is simply it, right? This is simply expected value from that. Okay? Is everybody understands? More or less? Okay, so this is sort of ideal function. It already has some error. Okay, so now let's see. But so if ideal function is part of my hypothesis space, that's great. But maybe it's not. Remember, I have this hypothesis space, the set of functions that I'm actually taking as candidates in my training process. Okay. So this is some, H, right? This is hypothesis space. It may include H squared, but more often than not, it doesn't include H squared. So it does include something that I call the best hypothesis, right? This is something like H star X function. So that's the best hypothesis that I can have from my hypothesis space. Okay, so H star X is simply the same thing as here, except I only take the functions from my hypothesis space. And then this stays the same. So this is the best function that I can get from my hypothesis space. And so that's so distance between this function and this function actually represents the error that I get from the fact that I have chosen some limited set of hypotheses, right? So for example, that's the error that I get from my linear regression. Any other source of error? Or is that it? Is H star X the representation of the error that we get in the end, in the testing? Or can it be even worse? Well, do you get H star X always from the training? No, you don't get it, right? Why? So basically, if you knew this distribution, right, completely, you could actually most of the time compute this H star X. But you don't know this distribution, just have a training data, which are samples from this distribution. So since training data, so we have some training data set, right? Training data set. We will call training data set capital T right now. And it's basically samples or some T samples from distribution Pxy. Okay? And so what we are getting in the training process, if we did it right, if we did the training right, we will choose the best function that can fit these T samples, right? So we are getting something like that. We will mark this function H hat. And actually, we will have a subscript T because it depends on the training set that we have got. Okay? And this function is simply the best function from H. But now we don't have this expectation. We only have some kind of estimate of this from these T samples. Okay, so instead we use sum of all the errors and maybe do 1 over t. So that's from all the, that's y. And so I'm also, yeah, I did not introduce the notation. So T is basically set of examples x1, y1, x2, y2, etc., xt, yt. Okay? So I have taken a training set from this distribution, selected like t different samples, and now as my training, the best I can do is just say, okay, find me the best function that fits this training data set. Okay? Which means find the function that minimizes the sum of errors on this data set. So that will be my h hat x, and it might be, you know, so that's my final function. And again, this introduces additional error. So now when I want to compute what will be, like I have this learning system, right? And I want to compute what's this, what will be some kind of expected error in the end. What do I need to do? Or what's the process by which I can do it? I have some size of training set T. So then I will select, basically, then I will select by independent sample. T training examples. I assume this is done by independent sampling from this distribution. Okay, so this is training example, training set T. Sample from Txy T times. So then I will, then I will train the function h hat. Okay, this is by choosing the best function from the hypothesis space that actually fits the data, the training data. But this is already, this is already a random variable, right? This function, because it depends on what I have chosen randomly here on the training set, which is also a random variable. And then finally, I get I just choose some kind of testing example. Okay, testing example. So this is x, y sampled from pxy. And now I look at what happens. I take ht hat x minus y squared, and this is my training. This is my testing error. Testing example, again, sampling from pxy. So
You don't know PXY.
you don't know pxy, but you assume, so this is already one part of the things that you need to think about when you are building your training testing sets. That you should get as close to this model as possible. So you should actually make sure that the samples, that the training data sets that we are getting are independent samples, if at all possible. Not, something like, I will just, I want to know political opinions of people in Slovakia, so I will ask lots of people in Bratislava, and that's it. Or maybe in Dubravka or whatever. Or I will just come to this faculty and ask students, right? That's the easiest. These should be independent samples, as close as possible as you can get. And, the new person who has the political opinion. It should also be an independent sample, so it should be somebody randomly chosen. And that's what you need to sort of think about when you are designing what are the training sets, what are the testing, what are the testing sets, and so on. So you don't need to know this distribution, underlying distribution. You just need to make sure that you are sampling, that the training set and testing set is sampled from the same distribution, and that these are independent samples as far as possible. And then this theory starts to work. Okay, so why we are doing all this? So in the end, I will have like some h hat p x minus y squared. That's what I have here, right? Testing error. So how do I choose the testing example? Well, it's easy. I'm choosing it as one of the, I don't know which one I choose, so I take expectation over all possibilities, right? So there should be a EXY of something like this, okay? Anything I'm missing? Well, I'm missing the whole training process right now in this, right? So I'm not only taking one random example, but I'm also taking random training set. So I have also expectation over all possible training sets. So that's my expected testing error. With the understanding that, like, once I have this training set t, I know how to get h hat t, the function. Okay, it's fixed. It's defined by the process. So in this is a random variable. This is a random variable. This is a random variable. So who understands what's written on the board now? This thing. Who understands that this is actually expected testing error? Okay, why not? What's the problem? Where did I fail? I'm just trying, here I have written some kind of process in the words. Okay? Get a training set, as independent samples from distribution, get h hat, get one testing example, and get an error. Okay? So you understand that process. And now I'm just writing the same thing in here, in expectation notation, nothing else. This is the same process as here, just rewritten in a more compact form. Yeah?
Expected value of an expected value?
Yes. Why not? Expected value is just a function. It's sum or integral or whatever of the values over some values. So it's just a function. You can do expectation of a function. Any other questions? So we have this expecting testing error. The question is how it's related to anything else. So let's try and do some tricks here. So I would really love to know how this actually relates to h star x, for example. Okay? So let's put it into somehow in the formula. How do you put it in the formula? Well, one possibility is to just, write it there. So it's the same like before. So the great trick that you can do is if you want to get some values inside the formula, you can add it and subtract it. You are adding 0, so that's 5, right? So like h hat x t y t x minus h star x, that's 1, plus h star x minus y, and this whole thing squared. Did I do anything intelligent here? Not really. I have just taken the same formula, subtracted h star x, added h star x, and did nothing else. It's the same formula. So okay, so if you started to think about what's like inside here, you can say, yeah, okay, so this is this thing squared plus this thing squared plus 2 times some multiplication. There is a non-trivial technical step which tells you this multiplication 2 times this thing is actually 0 when you take it over expectations. If you want to do it here, I will have a write-up for you as lecture notes on the website in a week or so. So basically, so this is not, there is a non-trivial technical step here. And this has something to do with the fact that lots of these things are minimums over some values and things like that. That they are not any arbitrary values, but they are related to each other. Okay? So it is no magic, and it's not true in general. It's true for these values. So I can decompose this into two things. So I have exy over e. I don't need to write this, all of this. H star x minus y squared. So this is this part. Okay. Plus exy e h hat h hat t. Oh, sorry, this is change of notation in my note. So this is ht. Why didn't you say it something? So htx minus h star x, and this is squared. And then, and so basically I have, what I have done, I have multiplied these two, or like this is something times something. I've done standard multiplication of the terms. I get this squared plus something else. And the two parts are here. This squared and this squared are here. And plus 2 times something is actually 0. And that's the part of this non-trivial technical step that I won't talk about at the moment. Okay, let's see what's interesting here. Any things I can simplify? Well, one thing that I can look at here, and I'm thinking about expectations over this. Does it have any t inside? Do you see any t inside? Training set somewhere inside here? This is all about the testing example, right? There's no training involved in here. So expectation over something unrelated is just, the same thing. So I can remove this thing. And in similar way, I mean, there is a, target variable y. Is it somewhere in here? Do you see it? So I can remove this. Okay.
It will be value of x, which is a single value number.
Yeah.
Adding it to a double?
Sorry? No, it's still single number. This is single number. So it's only, this says, I will take one pair xy from that distribution over there, and I will, compute this thing. Okay, this is still single value. Here, it says I will take pair from this distribution, but really I will not use the second pair of the pair, second part of the pair. So why I can ignore it.
How should you read it when there are extra
Expectation of an expectation? Stredná hodnota strednej hodnoty?
Mohla by tam byť započítaná.
Yes. There could be a parenthesis in there. I mean, this is nothing else. This is just a function, right? Which is dependent on some x here. And really, if you think about it, it's just sum or integral or something over some values. So it's nothing special. It's just some short notation that masks a lot of technical stuff, and also gives you some intuition about it. Sometimes wrong intuition. Okay, why is this interesting? Well, I mean, let's look at this thing. I have this picture here. This actually represents one of these errors in the picture that I have, right? Because this actually represents the picture that I get from the fact that I have chosen a particular set of hypotheses H. Okay? And so we call this term a bias. One note on this: if you had statistics and you were talking about bias and variance, this is noted by a bias and variance in statistical terms. So it just happens that these are things that are called the same way. Okay, so this is basically here bias means systematic error that I get from the fact that I have chosen a particular set of hypotheses. Okay, I cannot get the correct function or the one that I would like to because it's not in my set, and that's the part of the error that's coming from this thing. And then there is a part, this second part. This is actually called variance in this scenario. And if you look at this doesn't have anything to do with the correct function, with the h, h square or whatever. It just says how far my values that I'm predicting are from the best function that I could get from the. So this is sort of error that comes from the fact that I'm estimating the h hat from the limited set of examples. So this is somehow related to size of the training set and things like that. So let's say we have some fixed size training set, okay? So here we have you have graph with 2 coordinates. One will be generally some kind of error, okay? One of these terms that we are working here is. And here will be something like some abstract thing that I will call complexity of class of hypothesis. Complexity of H. Okay? So basically, you can imagine this as a, let's say, sequence of linear functions, quadratic functions, cubic functions, and so on. So with each of the steps, the set of hypotheses is getting bigger, and so it's getting more inclusive, potentially including h squared. Okay, so what do you think? How the bias will go? How it will look like? bias will go down. Why? Why?
We are still having higher chance to improve a
Well, I mean, we are taking the best function, okay? The function that gets you the best expectation over all the basically best expectation over all examples, right? So if you enlarge the h, you cannot get worse. You can only get better. So bias will always go down. Okay, so you start somewhere, and we will go down. It doesn't necessarily go to 0. Why? Well, it might be that in our particular progressions of more and more complex spaces, we actually don't have the right function a square included. It must actually go down as long as we assume that each next set of next h actually contains all the previous ones, is a subset, that they are sort of nested inside the other, then this must actually go down. So this is bias. So this is this error. How about variance? What do you think? You have fixed set of training examples. You are increasing complexity of h. What will happen with variance? What will happen with, how well are you going to be able to actually estimate? You have like 3 training examples, right? So linear functions you can estimate with 3 examples. Quadratic you can still estimate with 3 examples. Polynomials of size 3 or of degree 3, 4, 5, 6. That's going to sound like that's insufficient. Okay. So actually, if you keep the training set size the same, then you have more and more trouble getting close to the h star. Okay, and that's what this says. How far am I from h star when I train this? So the variance, I mean, this is just a hand waving at the moment, but I mean, but variance you can roughly see that it will go more or less up. So it will look something like this. This is variance. Now, what's the expected error? It's sum of those two, right? So at the beginning it will be high. Perhaps more importantly, at the end it will be high. And here, I mean, it will probably, I mean, these are 2 monotonous functions. There will be something like this. Okay, so when both of these are small, then you are getting small testing error, expected testing error. But once, like at the beginning, at the start with the less complex hypothesis, bias will dominate. With the more complex hypothesis, variance will dominate this sum. So this is expected testing error. Now this looks interesting. So if you had a particular learning system in mind, where would you, and you have all this information, where would you set the, where would you set the complexity of your class of hypotheses? Oh, you would you want most, like the minimum expected test error, right? So you want to set it here. So this is sort of right place where to have your learning system. And basically, every time you evaluate your learning system, you are trying to somehow from from some indications find out whether actually the bias is the term that dominates or the variance. So where if the bias is the term that dominates, you should probably increase your hypothesis space. If the variance is the dominating factor, you either need to decrease the complexity of your space or go hunting for more training examples. That's another option. Okay? Fine. And so we were talking at the beginning about some vague terms, underfitting and overfitting. So if I am here, this is called underfitting. If I am here, this is called overfitting. Any questions about this? So this is called one of the learning curves. There will be another one. Yes?
Why it's not possible to get bias to zero?
Why it's not possible to, well, it is possible to get bias to two things. One is there might be this inherent error. You can get multiple values. So the bias is two things together, right? One is the error that comes from the fact that the function is not enough to describe this space. And the second one is the difference between these two. The difference, the fact that h squared is not in our hypothesis space. So if you have hypothesis space complex enough that you can get h squared into that, you still can have bias coming from that part, from the other part. And under extremely unlikely conditions, you can get it to zero. Any other questions? So now, probably, one thing that I promised you is that we will actually talk about how the training is actually related to testing. And we actually didn't get there yet. And so the next question that I want to ask is how this actually have anything to do with the training. Where is the training error? Okay, so one technical thing, if you take h squared, it actually doesn't depend on the training set, right? H star doesn't depend on the training set. It only depends on the hypothesis space. So if I want to estimate what's the error on h star, then I may actually take an approach that I would like to, I don't need to estimate it on a training set. I can estimate it on any sample. So basically, what I'm trying to say is that if you take xy, if you take one sample and you take h star x minus y squared, then it's the same thing as if you take, if you estimate it over lots of training samples. It doesn't actually matter. So this says I'm estimating on the training set, randomly chosen training set, and I'm just estimating on one example, and it's the same thing. If you choose 10 samples independently and then compute average and then compute expectation over those, it's the same thing as if you would choose just any example and compute expectation over that one. Okay? So, okay. So why I am doing this? Now I have something like this. So I have 1 over t sum over. So let's take this thing. Let's take the So this is what? This is the training error, right? I'm taken from over all t training examples, I'm taking average over them. Okay. So I now can, again, using roughly the same trick as before. So I will take 1 over t. And now I will add and subtract something that I'm interested in. I'm interested in a dependency between h hat and h star. Okay. So I will into this I will insert h hat again, plus and minus the same thing, 0. So I will do h star x I minus h hat t x I, okay? And plus h hat t x I minus yi, and the same thing squared. Any questions so far? So I have just added the h hat and h hat. Again, if you do the same thing again, if you just try to expand this, right? You would get this thing squared plus this thing squared plus 2 times this times this. And again, with the same non-trivial step that I was talking about, you can show that this twice something is 0. So in fact, what you get is that it's equal to 1 over t sum I is equal to 1 to t h star xi minus h hat t xi squared, okay, plus 1 over t h hat t xi minus yi squared. What is this? It's the training. It's the training error, right? On a particular training set. So this is training error. And this is interesting thing. So this is something that so if I add expectations over this, I will get, let me write it down. Let me see, then I have space. So originally, I'm looking at this variance right over here. No, sorry, at this bias here. Okay? So this is Txy over h star x minus 1 squared. And so, putting this all together, I can say that this is expectation over training set instead of expectation over any sample. So this is T over, and here will be 1 over T sum h star x minus y squared. But I have now determine that this thing can be decomposed into these two things. Okay? So this is equal. So one is expectation over all training set of 1 over P H star xi minus H d xi hat squared. So this is this part plus et over 1 over t ht hat xy minus yi squared. So what does this mean? Well, so I have this. So this is bias, right? And I have decomposed it into two things estimated over training sets, which is a little bit surprising. So what is this? This is expected training error, right? Because it's a training error, but over all possible training sets. So this is expected training error. And this is something called, this thing over here is called training variance. So this is again some estimate on, how far I get from the training set, from the H star. Again, this goes down with this goes up with the increasing size of the hypothesis space and goes down with the increasing number of testing examples. So now, you can see, you have bias here. So there is another another curve somewhere here underneath, and it goes like it is actually increasing. That is expected training error. Expected training error is actually a little bit lower than bias. Okay, but perhaps what is more interesting is to look at how things develop when you actually fix the hypothesis space and instead change the number of training samples. Okay, so let's just draw one more picture and wrap up. So we have again error here. Now we have fixed hypothesis space H, and here we have number of training samples T. Okay, get this out. So the first thing we can notice is that bias has nothing to do with the size of the training set. It has anything to do. It only has something to do with the size of the training set, but nothing to do with the hypothesis space, but nothing with size of the training set. Okay, so it won't change with the training set. So bias will look something like this. So that's this term over here. Now, we know that bias is composed of training variance and expected training error. And we know that training variance, or we suspect that training variance actually goes to zero with the, or goes to zero with increasing the number of training examples. Basically, if you have enough samples from distribution, infinitely many, then you can estimate h squared with zero error. Okay? So that means that this looks something like this. So this is the expected training error. And this is training variance. The difference between these two. And again, on the other side, we have expected testing error is a sum of bias plus this other variance. Okay? So we have here, there is a variance between these two curves. And again, this variance goes down with the number of samples. So this is expected testing error. So what we have just shown is that expected that the training error and testing error will actually converge to the same value, more or less shown, with lots of them maybe in the middle. And it will converge to bias, basically, with the increasing number of training samples. So actually, the interesting thing is that when you increase number of training samples, you would expect things get better, right? But actually, from the appearances of all of these things, your training error will go most likely up with the number of training samples. But at the same time, the testing error will go down. The difference between training error and testing error will go down, and eventually they will converge on the bias. If you satisfied all the conditions that we had, all the spoken and hidden conditions that we had in this derivation. So what I want you to take as a message from this class, and we will review this at the beginning of the next class, is I want you to take with you these two pictures, this one and this one. Okay? This one tells you something about how the complexity of the hypothesis space is related to the performance of your learning system, and what you can do, and we will, articulate more clearly in the next lecture, what you can do to avoid this underfitting or overfitting, which are both bad. And this tells you something about how the training error and testing error will behave with the changing size of training sample. And again, that they will converge to some value, and that actually that seeing higher training error with increasing number of training examples is not a bad thing. It's something that you expect, actually. Okay, thank you very much. See you tomorrow.